this afternoon's session on optimization algorithms. We have several great spotlights and 2 oral talks. It's time to get started. I would like to have the first spotlight speaker come here. The spotlight talks will be 5 minutes each. There will be no questions. For the orals, we only have questions after the talk. Okay?
Hello everyone, I'm Zhide from Tsinghua University. I will talk about a simple proximal algorithm for non-convex optimization. This is a joint work with my advisor, Jenny. Let's look at the problem definition. Machine learning problems are usually modeled as an optimization problem. The goal is to find a good enough solution, such as the gradient norm is less than a small epsilon. Here we consider the more general non-smooth case. The objective function phi-x contains 2 parts, where the first part, fx, is possibly non-convex, and the second part, hx, is possibly non-smooth. The benefit of the second term is trying to deal with the non-smooth and constrained problems. Let's look at our result. We propose a simple proximal SVRG plus algorithm with a much simpler analysis and better theoretical results. In particular, it's more attractive in practice. It prefers moderate millibyte size, and more importantly, it can automatically adapt to the log coverage, which means during the iterative process, it can automatically switch to a faster linear convergence as long as this local region have a strong coverage. For example, locally strong convexity. We plot 2 figs to show our result compared with previous results. Let's first look at the left fig. It shows that our algorithm is better than the proximal GD, SGD, SVRG, and Saga. And as we mentioned in the last slides, our proximal SVRG plus algorithm prefers moderate millibyte size, which corresponds to the red box point at the bottom of the left fig. The value of this millibyte size is 1 over epsilon to the power 2/3. While the SSG algorithm prefers much smaller millibyte size, which equals to 1. And the original proximal SVRG algorithm prefers to a very large millibyte size, which equals to n to the 2/3. And for the right-hand figure, it shows that our algorithm uses less PO calls than the original proximal SVRG algorithm. And also note that recently, Zhou et al. And Fang et al. Improves the stochastic gradient complexity to square root n in the smooth setting. Our experimental results also validate our theoretical results, which shows that the proximal SVRG plus algorithm prefers much smaller millibyte size than the original proximal SVRG algorithm. And note that these 2 data sets are not very large. So if for a very large data set, the original proximal SVRG algorithm needs to choose a much larger millibyte size. And our algorithm performs much better than the proximal GD and the proximal SGD. Thanks. Welcome to our poster. And this poster number is the old version. Our new version is poster number 5. Thanks.
Hi everyone, I'm Insu from KAIST, and in this talk I will introduce stochastic Chebyshev gradient descent for spectral optimization. This is joint work with Haim Avron and Jinwoo Shin. Spectral optimization is optimizing some matrix functions. Here we focus on specific type of function called spectral sum. Given a scalar function f and a matrix A, it is defined that summation of f of all eigenvalues of matrix A. Depending on function f, it can be a broad class of matrix functions used in machine learning. Let me give some example. If f is log x, this is the log determinant. If f is power over p, this is matrix Shetland Pinom, general version of Euclidean. F can be also a step function, then it can be a matrix rank. Here we focus on minimizing spectral sum problem, assuming that matrix A is symmetric and parameterized. Also, we are assuming there is a simple function g, which means it is easy to compute itself and its gradient. Such a spectral optimization arises in many machine learning tasks, including collaborative filtering, hyperparameter learning, and also diversity modeling as well. To solve the optimization, gradient descent method can be used. However, computing the gradient of the spectral sum exactly have a cubic time complexity with respect to matrix dimension. This is expensive for large-scale matrices. Recent work on spectral sum approximation suggests that one can estimate the gradient in linear time with respect to number of non-zero entries of matrix A. This is much cheaper than the exact one. But this estimator is biased, which means for optimization, it hurts stable and fast convergence using stochastic gradient descent method. So we propose a fast, unbiased gradient estimator by revising prior method, and we provide convergence guarantees of SGD and SVRG, which is advanced version of SGD with reducing its variance. The prior method for spectral sum approximation is biased as they combining two approaches, which is randomized trace estimator and Chebyshev polynomial expansion. Since Chebyshev polynomial expansion truncates the series of f up to a certain degree, the remaining terms become the biased error. To solve this issue, we consider a randomized Chebyshev expansion by sampling a degree n randomly. Now, polynomial degree n is random variable, and we reweight the coefficient of Chebyshev expansion. It is easy to check that the randomized Chebyshev expansion is an unbiased estimator of function f, and this also makes the estimator of spectral sum and each gradient to be fully unbiased. Now, a natural question is, what is a good degree distribution? Okay. To this end, we aim for designing an estimator with small variance, which is expected to faster convergence using SVD. In particular, we consider variance minimization problem for given expected degree n. Without this condition, one can choose polynomial degree arbitrarily large, then variance of estimator can be arbitrarily small. So this assumption is is valid. Our main theorem is that degree distribution of following form has the optimal variance for the estimator, and using this optimal degree distribution, we can prove the convergence of SGD and SVRG. For example, our result for SGD shows a linear late in the result. We also apply our generic method to two applications, which is matrix completion and Gaussian process. Both programs involve in spectral sum optimization with square root function and log function. Our method of SGD is marked by yellow line and SVRG marked by red line. So as a result, our proposed algorithm runs at least 6 times faster than other gradient descent methods. If you have any questions or comments, please visit our poster number 6 tonight. Thank you for your attention.
Hello everyone, my name is Tianyi Chen. This is the work with Yorgos Giannakis, Tao Sun, and Wu Taoying. Our work is about solving the following optimization problem in parameter server setup. Each component of the loss function LM depends on the data stored locally at worker M and can be accessed only by worker M. The goal here is to learn a centralized model at the parameter server that can minimize the aggregated loss. So popular methods to solve this problem including gradient descent, which runs in an iterative fashion. However, in learning settings where the workers are mobile devices, such iterative procedure is not that effective because the uplink communication will become the bottleneck. So we developed a new method that can improve GD by achieving the same convergence rate, reducing communication complexity, and in practice, our algorithm can save more than 90% communication of GD. So let's revisit how GD works in this case. So at each iteration k, the server will broadcast the current parameter theta k to all workers. And the worker will receive theta k to calculate the gradient, upload the gradient to server. When server receiving all gradient, it will perform a GD update. In this case, GD will require m uploads per iteration, which is costly. So there are several work recently aimed to reduce the communication overhead of GD. For example, using the quantized gradient information, increasing computation before communication, or communicating gradient coordinates with large magnitude. However, most of these efforts aim to reduce the communication bit per round, but not the number of communication rounds. Therefore, our contribution is a new algorithm that can adaptively skip communication with provable communication reduction in terms of communication rounds. Our algorithm called lazily aggregated gradient, LAG, builds on GD. However, instead of requiring all workers to upload the gradient, LAG only selects a subset of worker MK to upload the gradient, and using the old gradient for the remaining workers that do not upload. Therefore, the key question here is how we can choose the MK in a way that it will not affect the optimization progress but save the communication. So we propose a simple way to select MK. So the idea is that whenever the worker M receives theta k, it calculates the local gradient and compare the fresh one with the old gradient stored in the local memory. If the difference between these two gradient innovation is large enough, in the sense that it's larger than the change of previous parameter update in the last iteration, then worker M will be included in a subset MK to upload the gradient. Therefore, the idea is that if the gradient innovation is large enough, then the worker will upload. If the gradient innovation is small, then it skips the gradient, the communication. Following the same principle, the right-hand side can be also replaced by the weighted average of the model parameter change. So our algorithm is very simple, but have strong performance guarantees. We consider 3 cases with different assumptions on the objective function. For example, non-convex, convex, strong convex, and smooth. In all these cases, LAG enjoys the same convergence rate as GD. In addition, the total number of communication uploads to achieve a certain accuracy on the LAG is less than GD and as small as 1/m fraction of GD. To highlight the performance of our algorithm, we implemented in linear regression case. And the left column of figure is the number of iterations, and the right column of figures are number of uploads. We can see that our algorithm requires similar number of iterations, but order of magnitude communication savings. And a similar phenomenon can be also observed in logistic regression case. Same number of iterations, but less communication uploads. Therefore, in our work, we propose a new way to communicate in distributed learning setup, and our algorithm does not degrade the convergence property of GD, but reduce communication overhead significantly. So for more details, please stop by during the post session tonight. Thank you.
Hi, I'm Geneviève Robin. I'm going to talk about main effects and interactions in data frames. And this is joint work with Otto Wai, Julie Joss, Olga Klopp, and Eric Moulin. So I want to start with an example. We're looking at water birds, so birds who live in wetland sites like ducks or flamingos. And most water bird species are declining worldwide. So an important question in ecology is to relate species abundance to factors like geographical and meteorological factors to understand this phenomenon. And to do so, we have access to two sources of information. The first one is a data frame that I'm going to call Y in the rest, and where the rows correspond to different geographical sites and the columns correspond to different years. So in every entry, I have an integer number, which is the number of birds that was counted in this site during this year. And there is a lot of missing values in this data frame. The second source of information are side information about the rows and columns. So I have geographical covariates about the different sites and meteorological covariates about the different years. And the goal is to estimate the effects of those covariates on the observed counts. That's what I'm calling main effects. And simultaneously, we also want to estimate some residual, and that's what I'm calling interactions. To do that, we introduce a general parametric model where every entry in the data frame Y follows an exponential family distribution, which is parameterized by an unknown parameter x, ij. So the main effects and interactions, they are modeled in the parameter space, so that for every entry, the unknown parameter x is the sum of a regression on the covariates u plus a residual L. And if we look at the matrix scale, we are decomposing a matrix of parameters, big X, into the sum of a regression on a dictionary of matrices that we are going to assume sparse, meaning that not all covariates have an effect on the counts, plus a matrix of interactions that we assume to be low rank, meaning that a few row and column factors summarize the interactions. The goal is to estimate the main effects alpha and the interaction matrix L, and we do that by minimizing a data fitting term, penalized by the nuclear norm of L, which induces low-rank solutions, and the L1 norm of alpha, which induces sparse solutions. And in fact, this estimation problem is a twofold generalization of a well-known problem in statistics, which is called sparse plus low-rank matrix decomposition. And it's a twofold generalization because first, in sparse plus low-rank matrix recovery, the sparse term is either entry-wise or column-wise sparse, while here it is sparse on an arbitrary dictionary of matrices. And secondly, the noise is not additive, it's in the exponential family, and it can be heterogeneous. So I don't want to give too much details about the theoretical results. What I want to emphasize is that the method we introduce is simultaneously statistically sound and computationally efficient. In particular, for the statistical guarantees, existing methods usually estimate main effects and interactions separately in the two-step procedure and don't have guarantees on the estimation of main effects, while here we have near optimal error bounds for the main effects and interactions simultaneously. And we solve the optimization problem with a mixed coordinate gradient descent algorithm, where the main effects alpha are updated with a proximal step, and the interaction matrix L is updated with a Frank-Wolf step, and we prove sublinear convergence of this algorithm. So now to conclude, I want to show numerical results which illustrate the theoretical guarantees. So on the top three plots, we are comparing our method, NeurIPS, which is in red, to a two-step procedure where the main effects and interactions are estimated separately. The first important result is that is for increasing problem sizes. So for large data frames, NeurIPS is faster than the two-step procedure, and the second important result is that our estimation error for the main effects is constant for increasing problem sizes, while it increases with the size of the problem for the two-step procedure. And finally, we compared low-risk in terms of imputation error to existing methods in ecology that are used to impute count data. And so our method is the green box plot on the bottom. And we show that it has a smaller imputation error, and furthermore, it is robust to large proportions of missing values. So thanks for your attention, and if you want more details, our poster is downstairs and it's the number 87. Thanks.
All right.
These are all the ones. Do you mind if I use mine?
We should have checked it earlier. Our next oral speaker is Kevin Scammon. This is one of the best paper awards, so I would like to present you
Thank you very
with
much.
this award. I would like to remind you that we will take questions after Kevin is finished with his talk.
Experiment. So, hello everybody. So this is a joint work with Francis Bach and Laurent Massoulier at INRIA and ENS, and Sébastien Bubec and... Wait a second. But, yeah, what? Okay. Yeah. Okay, sorry, I'll just take my computer. Okay, so that's much better. Sorry for the delay. Okay, as I was saying, this is a joint work with Francis Bach and Laurent Massoulier at INRIA and ENS, and Sébastien Bubec and Yintat Li from Microsoft Research. The idea of this work is to analyze functions which can be written as the sum of a function, several functions, each of them lying on a particular computing unit. So this is especially useful for empirical risk minimization that we want to solve in a distributed way. So distributed storage and at the same time parallelized computation. And you can think of, for example, logistic regression or stochastic or SVM or this kind of optimization problem in machine learning. So more specifically, we try to minimize an average of functions, and each of these functions lie on one of the computing units. We will make two different assumptions in this work. The first one is that the average function that we try to optimize is Lipschitz, and the second one is that all of the functions are Lipschitz and convex. So the second assumption is much stronger. And we will see that we can say a lot more in this second setting. Now, the way the computation is distributed is through a network of communications. So each node can, at the same time, compute gradients of its own function and communicate a gradient to his neighbors. Computation of a gradient takes an amount of time, 1 unit of time. And communication through the edges of the network takes a time tau. So we're interested in minimax convergence rate, so optimal in the sense that it's the best possible algorithm against the worst possible function, convex and Lipschitz. And there is a long-standing theory about these minimax convergence rate in optimization, well, single machine convex optimization.
there is a large panel of results about this. For example, there is a strongly convex and smooth setting and the Lipschitz and convex setting. For example, strongly convex and smooth, you can think about regularized logistic regression and SVM for the Lipschitz and convex. So one of our previous work of last year's ICML was to extend the smooth and strongly convex setting to distributed settings. Sorry. Okay. And the idea is that in this case, you just multiply the single machine optimization term by 1 plus delta tau, where delta is the diameter of the communication network, and tau is the time it takes to communicate from one node to his neighbor. So delta times tau just is simply the time it takes to communicate from one node to the most distant node of the network. And you can see that in the two settings that we considered in the previous paper, centralized and decentralized, the idea is basically the same, except that in the decentralized setting, we replace the diameter of the network by a notion of mixing time of random walks in the graph. So, of course, if you want more details, we can speak about it later in the poster. So the question is what happens in the Lipschitz and convex setting, in the non-smooth setting. And what happens is that it's not so simple. It's not such a simple setting. More interestingly, we find that actually the communication through the network is going to have an impact only on the second order term, which means that the blue term that you can see is the term which is related to the computation of the gradients, and the green term is related to the communication. The green term only depends on 1 over epsilon, whereas the communication term in blue depends on 1 over epsilon square. So this is a lower bound that we prove on the number of iterations required to reach a precision epsilon, but we also show that there is an algorithm which is very close to this. Unfortunately, it's not exactly the right convergence rate, and there is still a difference between the two. So the idea is an extension of a previously known algorithm, which is randomized smoothing by Ducci and his co-authors in 2012. And the idea is simply to smooth the objective function in order to have faster convergence rate. The idea is that you can perform this smoothing in a distributed way, and so you can trade off communication time for computation time in this way. What you can see here is that the convergence rate is going to have the right dependency with respect to computation time in blue, but there is an additive term in multiplicative term, sorry, in d to the power 1/4 in the communication time, where d is the size of the objective optimization problem. Okay, so in practice what happens, the idea is that we take a graph. We're first going to prune most of its edges in order to have a tree and to have efficient communication. And we're going to synchronize all the nodes by having the same random seed. And this is important in order to have the same random generator for all these, for all the computing units. Then the master node will send the current parameter, time t, and each node, each local node is going to first sample random points around theta t, compute the gradient, and average this gradient. So it's a very simple procedure, but if you choose the right amount of points, you end up with an algorithm which is close to optimal. So then it just sends back these averages, and the master node will make this average of all these values, and in order to get an approximation of the gradient of the smooth function. I think the strongest point, the most important point of this work is that this depends on the global Lipschitz constant, which means, and this can be much smaller than the local Lipschitz constant of all the local functions, because the global function is an average, so we tend to smooth the function. But unfortunately, it requires to know the whole communication network, and it's going to be it's not very robust to communication failures. Also, something to note is that the multiplicative factor, which is d to the power 1/4, in practice it's not so bad, let's say, even for relatively large problems, optimization problems. So even for d equals to 1000, we have d to the power 1/4, which is around 6. So it's a relatively small multiplicative factor. And in theory, we have some reasons to expect that this may be actually the optimal convergence rate. But this is future work. Okay, so now quickly for the second setting that we analyze, which is a decentralized communication scheme. The idea is that instead of having a master that is going to synchronize the communication, we now have a decentralized communication based on the gossip algorithm. So each node is going to broadcast a value and aggregate his neighbor's broadcast by a simple averaging scheme, weighted average. Now, if we do this, what we can show is that in this setting, we do have an optimal convergence rate, so matching lower and upper bounds. This is the lower bound, and you can see that here, basically it's the same as the global regularization setting, where we replace the global Lipschitz constant by the local Lipschitz constant, and the diameter of the network by this kind of mixing time, sort of mixing time, delta tilde. Which is actually in a lot of network, this happens to be very closely related to the diameter of the network. Okay, and the idea is that we use, it's an algorithm that we call multi-step primal dual, and this is similar to a recent paper of Lan and his co-authors in 2017. It's based on three important aspects. The first one is a primal dual reformulation of the problem. The second one is that we solve this saddle point optimization problem using Chambol-Poc. And the third one is that we are going to have an extra acceleration of the communication using accelerated gossip and Chebyshev polynomials. There is a lot of details that I do not have time to go into, but I will be happy to speak about this with you during the poster session. Okay, so in conclusion, what we show in this paper is an optimal convergence rate in one setting and closely related lower and upper bounds in the centralized convergence, the centralized setting. I think that the main message of all this is that in the non-smooth setting, early stages of the convergence are fast and they rely on an efficient communication. So here on the first stages of the convergence, the communication network plays a real role. Whereas for the later stages of convergence, you need the convergence will be slower and will not depend on the communication network. Okay, so thank you very much. I'll be in the poster number 10 if you have more questions about it.
Yes. So what happens if the communications are asynchronous?
Yes. So this is not something that we have looked at. So in the previous work, there was a possibility to make these random by looking at random gossip matrices. We haven't looked at this case if it also works as easily in this setting.
Have you considered the communication with a parameter server?
Is what?
With parameter server, like there's a different set of machines to store the parameters.
Okay, so you have machines to store the parameters and machines to do
like
the communication?
In TensorFlow or Disbelief, we have parameter servers.
Mm-hmm.
So have you considered those cases?
So I guess that in these cases you would have a bipartite network and it would change the structure of the communication network. That would be one way to describe it. But I guess you could have also a more detailed description of the problem if you specifically look at algorithms for this setting.
Thank you.
All right, let's thank Kevin again, also for his best paper award. Good job.
Okay, thank you. Good afternoon, everyone. It's great to be here. I'm going to tell you about the work of my student Jingzhao Zhang, my postdoc Aryan Mokhtari, and my colleague Suvrit Straw at MIT. Unfortunately, the first two authors couldn't be here because of visa issues. Hopefully, we can fix this. So I'm going to tell you about a way of getting acceleration in first-order convex optimization by directly discretizing a continuous time ordinary differential equation. To do that, I want to tell you a little bit of background. Of course, a lot of you know about acceleration. First-order optimization, as you saw, is our method of choice. If we want to optimize a smooth convex function, typically what we do is we take the gradient, we take a step along the direction of the gradient. If we take the step size to 0, what we recover is the well-known gradient dynamics. And of course, we know that as we saw in the previous talk, the convergence time for a smooth convex function is 1 over t. Now, if we want to accelerate this, we can use the celebrated Nesterov's accelerated algorithm, which is essentially, as we all know, a reformulation, a very nice, clean reformulation of Polyak's heavy ball method with subtle differences. And so you now add a momentum term, and you evaluate gradient at this midpoint term y. And of course, we also know, as of a few years ago, thanks to this work of Sue, Boyd, and Candace, that essentially we also recover an ODE if we take the step size to 0. Now, this ODE is our heavy ball ODE, except that the friction term is not constant, but it's time varying. Okay, so this is what we know so far. So what is this talk about? This talk is mostly about how do we go the other way. How can we take the ODE and get an algorithm out of it? And I'll talk about some of the subtleties in here. And of course, we know that this algorithm achieves the optimal rate of 1 over t squared. So if we take this problem in continuous time, we can, as we've sort of seen in this now famous paper by Wibisono, Wilson, and Jordan, we can essentially speed up things in continuous time as fast as we want by rescaling time. Okay, and so we can go from 1 over t squared in continuous time to 1 over t to the p. The challenge is that when we discretize, we can't do better than 1 over t squared. So the issue here is that if we want to get fast rate, we have to do a faithful discretization. But if we want to prove stability of the discrete algorithm, then we have to make the step size small. So this is really the difficulty in here. So how can we relate the convergence rate in continuous time to the convergence rate of the discrete optimization? So what we're going to do is we're going to show that, contrary to some of the suggestions in the existing literature, you don't need any specific integrator that preserves the mechanical properties, at least in certain special cases, to achieve acceleration. So you can use good old Runge-Kutta integrators, and we show that, in fact, it's the order of the integration scheme plus a notion of smoothness of the function around the minimum, or flatness of the function, that matters. So we'll define this in a second, in the remaining minute. But essentially, our main theorem is that you can achieve acceleration by discretizing this ODE if your function is s plus 2 differentiable and convex, where S is the order of the Runge-Kutta discretization scheme, and it's P flat. So P flat means that the first non-zero term of the Taylor expansion of the function around the minimum is of order P. So P equal to 2 is the standard case that we look at. There's a typo here for P equal to n. That should be the logistic function log of 1 plus e to the x. But essentially, what the key challenge here is to bound the discretization error. So if you know that the higher order terms of the function are bounded, what you can show here is that you can also beat the 1 over t squared bound because you know more about the function. You're still using first order information, but you can actually achieve faster and faster rates by better and better integrations. I'll be happy to tell you about the details. We're poster number 9. Thank you.
Hi, I'm Madeline Udell from Cornell. This is joint work with Swati Gupta and my student Songjo, who couldn't be here today, also due to visa issues. So I'm here to tell you about how to minimize, once again, a composite function. It's the sum of a strongly convex function g and the Lovász extension of a submodular function f. For this talk, what's important about the Lovász extension is it's a piecewise linear convex function that generically has exponentially many pieces. These functions generalize the L1 norm. They're useful for regularizing a lot of learning problems. So these functions are, these problems are generically have exponential representation complexity. But we're showing you how to solve them using linear memory and getting linear convergence when G is smooth and strongly convex. To give you a little bit more details, we're going to use a dual view of the Lovász extension. We'll define the base polytope of the submodular function, which is a polytope that generically has exponentially many vertices and exponentially many facets. You can define the Lovász extension equivalently as the maximum of the linear function x over the base polytope. This is useful because linear optimization over the base polytope is easy. Using Edmonds' greedy algorithm, you can do it simply by sorting the elements of the vector x and evaluating the submodular function n times. That's important because often submodular function evaluation is hard. So we want to solve our problem by evaluating the submodular function as few times as possible. So this means that we can evaluate the Lovász extension and its subgradient easily. Okay, the original simplicial method is one method for solving these problems that was proposed by Francis Bach in 2013. The idea is that f is piecewise linear, so we can approximate it with a piecewise linear function that has fewer pieces. We'll choose a function that matches the value and gradient of f at each of the previous iterates. We'll minimize g plus that approximation to f to determine the next iterate. One advantage is that it has finite convergence, but since this piecewise linear function f might have exponentially many pieces, it can take, it's not clear that it converges in a fast number of iterations, and the subproblems get larger and larger and larger at every iteration. Okay? We made one change to this method, which is instead of keeping all of the pieces of the approximation, we only keep the ones that are tight at the current iterate. So we drop the subgradients that are not tight at the current iterate. Let me show you how this works. So here the black function is our function g plus f. The blue function is our approximation to f plus g. So although the approximation to f is piecewise linear, the result of g plus the approximation to f is smooth. We minimize the approximation, get a new iterate. We evaluate f and its subgradient at the new point, add it to the approximation. We get a new approximation, the blue line, minimize it, compute its the value and subgradient of f at the new iterate, add it to the approximation, continue. So here everything's normal, right? The lower bound keeps getting tighter. At the next iteration, though, the far left part of the approximation is no longer tight at the current iterate, so we drop it. The approximation gets lower. Okay? Now that the approximation is not monotonically increasing, it's not even obvious that this method converges. Okay? But in fact, it does. We're able to show we still have finite convergence. We can show we have a limited memory, so the number of pieces of this piecewise linear approximation is bounded by n plus 1, where n is the dimension of the space. And in fact, we can show linear convergence as long as the convex part G is smooth and strongly convex. Okay, to explain how this works, we took the dual view. So we considered a dual algorithm for the dual problem, which is to minimize the Frenkel conjugate of G over the submodular polytope, the base polytope. Okay? Let me show you how this method, and so it's a limited memory version of fully corrected Frank-Wolf. I'm going to show you how it works. At every iteration, you take a current active set of vertices. Suppose it starts with V1. You compute the negative gradient at that vertex. You add it to the active set, and you exactly compute the minimizer of the function G star over that set. Next iteration, I compute the gradient, take the vertex that maximizes the inner product of the negative gradient, add it to the function, I get the new iterate. If that iterate is inside, strictly in the interior of a full dimensional space, then I must be done. I've solved the optimization problem. Okay? Otherwise, I'm at the boundary of the face. What does that mean? It means and I can compute the gradient at that point. It's pointing out of the convex polytope of the current set of active vertices. This means every vertex that's not on the active face is suboptimal. Okay? So I can drop that vertex and continue on. This shows that the number of vertices in my set is always bounded by n plus 1. Okay? This gives me the limited memory property. I have linear convergence using theory from Lacoste, Julian, and Yagi in 2015. And furthermore, we were able to show that we have duality between these algorithms. Limited memory fully corrected Frank-Wolf is dual to limited memory Kelly's method in the sense that the iterates match at every iteration. So they have the same convergence properties. Thanks. If you want to know more, see our poster, which is number 16, downstairs.
Hello, everyone. This work is called Probably Concave Graph Matching, and this is joint work with my advisor, Yaron Lippman. So graph matching is the problem of finding meaningful correspondences between nodes of two graphs. And usually, we represent graphs as affinity matrices. Here we use A and B, and we are looking for a permutation matrix X that encodes an optimal map between the nodes. It is pretty popular to represent or formulate such problems as the following quadratic assignment problem. And as you all know, this problem is NP-hard, and one popular way to deal with it is by relaxing the constraints to the convex hull of permutation matrices, which is called the set of doubly stochastic matrices. So all this is well known, and many papers have already dealt with this situation. We will mention two. So Lizinski et al. Show that for a certain class of graphs, the minimizers of the relaxation and of the original problem are exactly the same. And Westner, Boyarsky, and colleagues show that for specific choices of the affinity matrix, the energy is concave. And showing a relaxation is concave is significant since it implies that all local minima are permutation matrices. It also implies that the solution set of the relaxation and the original problem are exactly the same, and this is a plausible, something we want from our relaxation. Okay, so the main contribution of our work is showing that many important graph matching problems are concave, and this includes matching problems in which the affinities represent Euclidean distances as well as geodesic distances on surfaces. So the first question I want to ask is which affinity matrices give rise to such concave relaxations? And the answer is pretty simple. It is summarized in the following theorem, which states that all we need is, or it is sufficient that the affinity matrices A and B are generated using positive definite functions of order 1. And the main idea behind the proof is that we only need the energy to be concave or negative definite on a strict subspace of all the matrices. Using this theorem, it is pretty straightforward to show that any matching problem in which the affinities describe Euclidean distances or spherical distances in any dimension results in a concave matching problem. Okay, so the next question is, do we really need a concave relaxation? So in order to generalize further, we would like to relax this concavity constraint a bit. And our motivating example in this case is replacing the Euclidean distances we have just seen with geodesic distances on surfaces. And in this case, we empirically observed that the energy is not concave, but it is really close to being concave. It's almost concave, which means that it is very rare to find a direction in which the energy is convex. So in order to quantify this notion of almost concavity, we define or we devise an upper bound on the probability of a matrix being positive definite on a randomly sampled subspace. And for example, we can use such a bound in order to show that the matrix with the slight negative spectral bias is actually negative definite in practice for large enough M. We use this theorem in order to show that many useful energies are concave with high probability, which implies that they enjoy the advantages of concave relaxations with high probability. In the paper, we use all these relaxations for two main applications. The first is non-rigid shape matching, and the other is shape space analysis. And you can see all the details in the paper. To conclude, we've shown that there's a large family of concave or probably concave relaxations for matching problems. And we've also shown that checking if a specific functional is probably concave is pretty easy with our eigenvalue bound. And lastly, we extend the theoretical results of Lisinski et al. To practical matching problems involving distances. Thank you.
Hi. So there's currently a great amount of interest in parallel stochastic optimization with a huge number of parallel algorithms being proposed in a variety of what I'll call parallelism scenarios. And these correspond to a variety of situations from multiple processors on a single CPU to federated learning in which millions of cell phones are scattered all across the world. So there's all these different parallelism scenarios with different algorithms giving different guarantees. And what we try to do here is understand when are these algorithms optimal, when are they not optimal, and what can we hope to improve them by? So to answer this question, we formulate an oracle model which can be used to study parallel optimization algorithms. In particular, we use a dependency graph, a directed acyclic graph, in order to capture the allowed structure of an algorithm's oracle axes. So each vertex in this graph corresponds to a single oracle axis, for example, a single gradient query. And that oracle axis must be computed as a function only of oracle axes and ancestors of that node. So in this way, we can take this parallelism scenario and formulate it in terms of a particular graph. And we can use this oracle model in order to study a variety of parallel optimization problems. And we can rephrase our earlier question as, in a particular parallelism scenario, as captured by a particular graph, what is the best we can hope for? To answer this question, we prove lower bounds in terms of two simple properties of the graph: the size, which is the total number of oracle axes, and the depth, which is the length of the longest directed path in this graph. So we prove lower bounds for convex optimization using both a stochastic gradient oracle and also a stochastic prox oracle. So what can we do with these lower bounds? Well, for a number of interesting problems, we can use these lower bounds in order to establish the optimality of existing algorithms. But today I'm actually going to focus in on a situation in which these lower bounds expose gaps in our understanding. So the intermittent communication graph corresponds to a situation in which M machines make K parallel oracle axes between rounds of communication and communicate T times in total. So plugging these parameters into our theorem, we get the following lower bound for first-order stochastic optimization. So one algorithm that can be implemented on this graph is accelerated mini-batch SGD, where one mini-batch gradient is computed for each round of communication. And this gives the following guarantee on the error. So as you can see, the second term of this guarantee matches the statistical term of the lower bound, but the first term fails to match the optimization term. And this raises the question of whether we can improve upon this algorithm. And the answer is that we can. So in another regime, it actually makes sense to simply ignore M-1 of the available machines and just do plain old SGD on the remaining machine. This gives another guarantee. And in a certain regime, this improves upon the previous algorithm and matches the lower bound. But in another regime, it does not. This again raises another question, which is, can we improve upon both of these algorithms? And again, the answer is that we can. So if we use SVRG in order to optimize an empirical objective, we can get another guarantee, which again, in a certain regime is better than the previous algorithms and matches the lower bound, and in another regime is not. So we can look at the combination of all three of these algorithms to get an even better guarantee. But it still does not match the lower bound in all parameter regimes. Therefore, our study of lower bounds in this setting has exposed a couple of gaps in our knowledge. So the first is that we don't have any algorithm whose guarantee matches the lower bound, and therefore we can't conclude that we have an optimal algorithm for this setting. Second is we don't even really have a single algorithm that gets the best known guarantee in all regimes at the same time. We sort of have to rely on this combination of three different algorithms. And finally, this is not even mentioning the fact that the most obvious and natural algorithm for this setting is parallel SGD. And unfortunately, existing analysis of parallel SGD is somewhat unsatisfying, and in particular does not improve upon accelerated mini-batch SGD. Therefore, a better, tighter analysis of parallel SGD is required. And to talk about this more, I'm poster number 11 downstairs.
All right. Our next oral talk will be given by Sami Jelassi on the smoothed analysis of the low-rank approach for smooth semi-definite programs. I again remind you that the questions will be taken at the end. Take it away, Sami.
Hi, everyone. So my name is Sami Jelassi. I'm a PhD student at Princeton, and I'm delighted to present the work that I have done with my two collaborators, Thomas Pumir and Nicolas Boumel. And today, the main topic of my talk is going to be about a class of optimization problems that is called semi-definite programs. So people got interested in this class of designer problems for many years now, trying to develop the theory and designing algorithms, because actually you can find semi-definite programs everywhere. For instance, in robotics, in the case of the simultaneous localization mapping problem, or also in machine learning, in the case of the k-means and maximum variance unfolding problems, but also in other classic problems, such as the committee detection problem in the stochastic block model, or when you want to solve the phase ratio problem in molecular imaging, or when you want to find the maximum cut in a graph. So in particular, all these problems share a common property, that is, if you want to solve them mathematically, you have to write down a nonlinear optimization problem. But solving nonlinear optimization problems is quite difficult, so one way to deal with that is to write a semi-definite program, to relax your problem as a semi-definite program. And once you know that you have a semi-definite program, this is very nice because you have a convex problem that can be solvable in a polynomial polynomial complexity, and you have a solution of the relaxation. And in most of the cases, the solution of the approximated problem is helpful to understand the original problem. So as you see, semi-definite programs are powerful. However, they have a main inconvenience. What is inconvenient is that they are not scalable. And this is a problem in machine learning because we have a lot of data. And in the first part of my talk, I'm going to present a scalable method to solve efficiently semi-definite programs that is known under the name of Bura-Montero method, and that has been discovered in 2003. And then, and this is the main contribution that we make in our paper, I'm going to present some new theoretical understanding for this method. So first, let me introduce this semi-definite program. So as you can see, this is an optimization problem where you are minimizing a linear function, c dot x, subject to linear constraints. And here, as you can see, you have a convex problem. And it turns out that this class of problems is interesting because in many situations that you encounter in practice, you can relax or express your problem as a semi-definite program. So let me introduce one example, the phase ratio problem. So this is a signal, this is a problem that you find in molecular imaging or in physics. And this is a signal estimation problem where basically the signal here is a vector. And what you're observing is a bunch of quadratic measurements of this vector. And mathematically, what you have to do is to solve a system of quadratic equalities. So this problem in general is known to be hard, but turns out that you can relax this problem as a semi-definite program. A semi-definite program, you are happy because this is a convex problem and you can have the solution. So here we did some numerical experiments and we used a dedicated interior pond method to solve the problem. And as you can see, as the size of the problem grows, the amount of time to solve the problem grows out of hand. So for instance, when you have an instance of 3,000 data points, you are spending 7 hours to find the solution. And I would like to add that when you have 10,000 data points, actually the algorithm is running out of memory. The method that I'm going to present in the next slide is what is called the Birra-Montero method, and it is able to solve the same problem with the 3,000 data points and reach the same solution in 11 minutes. So basically, we are doing 40 times faster. And this method has been discovered by Birra-Montero in 2003, and the principle is the following. So since the matrix X is positive semi-definite, you can decompose X as equal to YY transpose, and replace X by YY transpose in the original semi-definite program, and you obtain a new problem. So the new problem is minimizing a quadratic function C dot YY transpose subject to quadratic constraints. So the first thing to observe is that we switch from this semi-definite program, where we had to optimize a big matrix X, to a new problem, where the optimization variable is a narrow matrix Y of size n times k. And k here is a parameter that is controlled by the practitioner. So there is an incentive to take k as small as you can. However, I will show you in the next slide that you cannot take k as small as you want, but we can still take k much smaller than n. Moreover, as you can see, we don't have to enforce the fact that the matrix is positive semi-definite, because it's naturally enforced here. So this is contrary to the original semi-definite program, and this is very nice because standard algorithms that enforce that the matrix is positive semi-definite are known to be of cubic complexity. So as you can see, this problem seems to be very attractive from a computation point of view. But the problem that you have a price to pay, and the price to pay here is that you are losing the convexity property. So this problem is non-convex because the inequalities are quadratic. And in other words, when you run any standard optimization algorithm, you are not sure to find the global minimum. So how can we choose k? There is a theorem by Vervinok and Pataki from the 90s saying what is the right choice of k in general. Under my assumptions, the solution of the semi-definite program X can be rewritten as X equal to YY transpose, and Y here is of size n times k. And k here is of the order of the root of the number of constraints. So what this theorem says is that if we are able to find the global minimum of Birra-Montero, then we are able to find the minimum of the semi-definite program, and we are happy. So in other words, this reduction from the semi-definite program to the Birra-Montero problem is meaningful with k small. Once again, the problem is that Birra-Montero is not convex, so you don't have any guarantee that we recover the global minimum. So despite this non-convexity problem, what has been observed in practice is that Birra-Montero scales well and gives very good results. So it has been successfully applied to many machine learning problems, such as the k-means clustering problem or the maximum variance unfolding problem. And the question that I would like to tackle in this talk is, can we explain this good performance that you observe in practice? In other words, is this non-convexity a real issue? So first, let me explain you a little bit what has been done in this line of research. So just to sum up, we started with a semi-definite program that is convex, and the problem with semi-definite programs is that they don't scale well. We switched to another problem that seems to me be more attractive from a computational point of view, that is this Birra-Montero problem. And the issue with this Birra-Montero problem is that it's not scalable. So you don't have any guarantee to find the global minimum. However, what has been showed by Bumal, Voroninsky, and Bandera in 2016 is that for almost all cost matrices C, the landscape of Birra-Montero is going to look like something as you see in this cartoon. So as you can see, this landscape is non-convex, but there are no spurious local minima. So when you run any standard optimization algorithm, you're expecting to find the global minimum. However, the result holds for almost cost metricity. It means that you have the possibility of bad cost metricity. And what is this bad case scenario? You can have areas where you have approximate spurious local minima. And when you run, for instance, gradient descent, you're running gradient descent for a finite number of iterations. And there is this dangerously flat area where the gradient can be very small, and your gradient descent iterate can get stuck in this area. And you are not happy because this iterate is far away from the global minimum. So this is a problem. And the way we tackle with this problem is by doing the following. So we say that even though there are this bad case scenario that can happen, if we add a small perturbation to the cost metric C, then we switch from a landscape that is not nice to a landscape where we don't have these tricky areas, and where we can safely run the standard optimization algorithm. And this idea amounts to what is called smooth analysis. So smooth analysis is something that is hybrid between worst and average case analysis, and the idea here is that we know that there are this bad case scenario, but what we would like to argue is that this bad case scenario is quite rare, and in most of the cases we don't have it. So, and the idea that we do in our that we implement in our paper is that we add a small perturbation to the cost metric C, and since we know that the set of bad cost metricity is small, then with high probability, if you add a small perturbation to the cost metric C, then with high probability you will not be in this worst case scenario. So I would like to mention that this idea has been already used by Bojana Pali and co-authors this year. So as us, they did the smooth analysis for the semi-definite program. And what we do, and this is what I will explain in the next slide, we're making an assumption on the class of semi-definite programs that we look at. In their case, they're making much weaker assumptions, but the price to pay is that the constraints are enforced through a quadratic penalty. In our work, we are making an assumption on the class of semi-definite programs, but at least the constraints are exactly satisfied. And the assumption that we make is the following, that is called the smoothness assumption. So if you look at the Breuer-Montero problem and you look at the feasible set, what we assume is that this feasible set is going to define a smooth manifold. So a smooth manifold is intuitively a space that looks like an Euclidean space locally. And actually, this assumption is not too crazy because many of the semi-definite programs that I mentioned in the introduction satisfy this condition. Okay, just to conclude, so here's the main contribution that we make in our paper, and if you want to have more details, please don't hesitate to come to see our poster. So what we show in our paper is that under some assumptions, if you look at the perturbed version of Breuer-Montero, and you look at the approximate second-order points of this perturbed Breuer-Montero problem, these points are going to map to the approximate solution of the semi-definite program. And this result holds with high probability under perturbation and with k not too large, so k of the order of the root of the number of constraints. And the reason we are looking for approximate points is just because when you run these optimization algorithms, they return you approximate points. So in other words, if there is only one thing to take from this talk is that if you are facing with a semi-definite program, in most of the cases, it's worth to solve the Breuer-Montero problem. And if you have more questions, please come to our poster. We are poster 3 in room 210. Thank you very much for your attention.
Any questions for Sami? So let me ask you a question.
Yes.
So for the Breuer-Montero approach, is there any actually complexity result for the algorithm itself? Because you mainly focused on the criteria, and then you established that under the smooth manifold assumption on the constraint set that there's no local minima and you should be able to find it. But like, is there any algorithm that has a
So in practice, to solve this Bermond-Zero problem, what we use is what is called Riemann trust region algorithm, and there are complexity results that are known for this algorithm.
Okay, those require projections on constraints.
Yes, exactly.
If there are no questions, let's thank Sammy again for this talk.
Hi. So my talk today is about Wasserstein-Kalman filtering, and this is a joint work with Peyman Mohajirin Esfahani from TU Delft and Surush Shafi and Daniel Kuhn from EPFL. Consider the problem of estimating a signal X from a noisy measurement Y. The classical minimum mean square error estimator is defined as a function psi that minimizes the expected square error between the signal X and its prediction psi of Y. This expectation is evaluated under a nominal distribution P that represents the prior information about the stochasticity of X and Y. We assume here that P is Gaussian. This estimation problem actually is very sensitive to perturbations to the distribution P. As such, we propose to find a robust estimator that minimizes the worst case expected error over all distribution Q in an ambiguity set. We define the ambiguity set as a ball in the space of distributions using the Wasserstein distance. The squared Wasserstein distance between Q and P can be defined as the minimum transportation cost of moving Q to P, where the cost of moving a point mass is given by the squared Euclidean distance. More precisely, we define our Wasserstein ball, our ambiguity set, as a Wasserstein ball with radius rho that contains only normal distributions. The proposed distributionally robust estimation problem can be interpreted as a zero-sum game between a statistician and an adversary or nature. This problem turns out to be notoriously challenging because psi lives in an infinite dimensional functional space, and the problem turned out to be non-convex. Fortunately, we still managed to establish the following structural results. First of all, we prove a minimax theorem that justifies the interchange of the infimum and the supremum operator. As such, the optimal robust estimator that solves the minimax program and the least favorable prior that solves the dual maximin program form a Nash equilibrium. Second, we show that the optimal robust estimator is going to be a linear function of the measurement, and the least favorable prior is going to be a normal distribution sharing the same mean with the nominal distribution. As such, finding the optimal robust estimator is now equivalent to solving a nonlinear semi-definite program. Third, we are going to devise a Frank-Wolf algorithm to solve this SDP, and we show that the Frank-Wolf algorithm is highly efficient because the direction finding subproblem admits an analytical solution. And finally, we show that this algorithm has a theoretical convergence rate of 1/k. We apply our results into the context of Kalman filtering. The classical Kalman filter iterates through repeated update and prediction step. At any time t, the prediction step generates a prior distribution, which is a Gaussian distribution with mean mu t and covariance matrix sigma t. The update step then generates a posterior state estimator based on the observation yt by solving a classical minimum mean square error estimation problem under PT. The Wasserstein-Kalman filter replaces this classical estimation problem with a distributionally robust estimation problem, which uses the nominal distribution PT as the center of the Wasserstein ambiguity set. And then the update step then used the optimal robust estimator to generate a robust state estimate. We now showcase to you some numerical results of our Wasserstein-Kalman filter and the estimator. The left graph shows that the distributionally robust estimator generates lower regret than the classical estimator, comparing to an ideal estimator that possesses full distributional information. The graph in the middle shows that the Frank-Wolf algorithm actually has an empirical convergence rate of 1/k squared. Apologies for the typo here. Finally, the graph on the right shows that the Kalman filtering, the Wasserstein-Kalman filtering, has better performance than the classical Kalman filter, and it also outperforms the Kalman filter using the Kuhnbeck-Leibler ambiguity set. If you want to know more about the power of distributionally robust estimation, please feel free to pass by our poster at number 14, and we are happy to entertain you. Thank you very much.
Hello to everyone. My name is Pavel Dvorechensky. This work is on a new decentralized distributed algorithm for Wasserstein barycenters. And it's a joint work with Darina Dvinskih, Alexander Gasnikov, Cezar Uribe, and Angelia Nedic. So Wasserstein barycenter is defined as a minimizer of sum of Wasserstein distances. And one of the application examples is analysis of data with geometrical structure, for example, images. So I like this example from Couturier-Dasset paper from 2014, where they showed that if we want to reproduce a template from its random transformations, then the best answer is given by Wasserstein barycenter. So we consider this problem in a semi-discrete case. This means that we want to find a discrete approximation for the barycenter. We also introduce entropic regularization, as it's usually done in the literature. And so our problem becomes this finite dimensional minimization problem. We consider it in the case of large scale, so the n, the dimension of the support of the barycenter is large, and also the number of data is large, so this is m. And two other challenges are that the data can be produced and stored distributedly. For example, it can be produced by a network of sensors, and we cannot have it on one single computer. And another challenge is that the measures for which we want to calculate the barycenter can be continuous. So here is a short review of the literature. So Sinkhorn-based algorithms are quite efficient for large-scale problems, but it's not clear how to apply them for the distributed setting and for continuous measures. And the questions of complexity is open. On the other hand, recently it was shown that accelerated gradient descent can be a good alternative for calculating Wasserstein distance. And accelerated gradient descent, so as we saw from the Kevin Skammer's talk and other papers, they have a good extensions for decentralized distributed setting, but they're not directly applicable for the case of continuous measures for this Wasserstein barycenter problem. And thus, the complexity for the case of continuous measure is also an open question. So for continuous measures, they will propose some algorithms which are based on stochastic gradient descent, and they even are parallel algorithms. But the difference with our setting is that these parallel algorithms use only a specific distributed setting. So they are specific to so-called star topology of the graph. But we want to solve it on a general graph. So we combine in our work all these four desired features and also provide complexity estimates. So to do so, first we consider a general optimization problem with linear constraints and provide an accelerated primal dual stochastic method. The main difference with the literature is that in our case, the dual problem is a stochastic optimization problem. And we need not only to solve it, but also reconstruct the solution of the primal problem. So we obtain complexity estimates. And so this algorithm is of independent interest. And then we apply it to the decentralized distributed setup and provide an algorithm for distributed calculation of Wasserstein barycenters together with complexity analysis. And we also present some experimental results. So we follow the framework which was mentioned in the Kevin Skammer's talk and which appeared in their paper, and in the paper by Lan and co-authors, and in the paper by Uribe and co-authors, all 2017. So the idea is that we want to minimize the sum of functions. Then we introduce some auxiliary variables, x1 till xm, and obtain a separable objective function. So then communication constraints are written through the Laplacian matrix. And finally, we have a separable minimization problem with linear constraints. Then the idea is to write the dual problem and solve it. So the main difference in our case is that the dual problem is a stochastic optimization problem, and we not only need to solve it, but we need to reconstruct the solution of the primal problem, which is a barycenter. So this is more or less a repetition of what Kevin told about. So each node calculates a stochastic gradient and then broadcasts it to the neighbors. And each neighbor, by aggregating the gradients of the neighbors, obtains a descent direction. So we introduce acceleration and primal dual analysis. So for details on the theory and practice, please come to our poster in the evening.
My name is Yao. I'm assistant professor at Georgia Tech. This is a joint work with my student Lian and colleagues at Georgia Tech. So what is the motivation? So we're particularly interested in this problem where you can have a binary classification and you have one particular class where both classes have very few data points. Where does this problem rise? It arises very commonly from problems such as anomaly detection, where you have very few cases, very few data points for anomalies. Maybe you have lots of training data for your normal cases, but not for the anomalies. And for healthcare applications, where you can have lots of samples for normal people, but not many for positive cases. So what is the difficulty for this unbalanced or limited data case? Is, it's hard to find optimal detectors or optimal classifiers. And coming from a statistics and optimization background, so in my view, I think the optimal one, should come from Lin and Pearson. You should look at the likelihood ratios. But the difficulty is, if you look at a limited sample case, it's harder to estimate the parametric cases in high-dimensional case. And if you look at empirical distributions, the empirical distribution may not have the same support. So if you take a likelihood ratio, you will have numerical problems. So it's impossible to perform the optimal Neyman-Pearson test. So our formulation is the following. Consider we view the classification as a hypothesis testing problem. Given a sample, you try to determine which of the hypotheses is true. And we believe the true distribution P1 and P2 are within certain uncertainty sets. So this calligraphic P1 and P2 are uncertainty sets for distributions that are centered around the empirical distribution from your data. And it's important here that we construct these uncertainty sets using Wasserstein metrics. And the reason we consider Wasserstein metric is similar to the other cases before is because Wasserstein metric allows for different support. So you can move the masses around in order to achieve this. So you can have points where you don't have any observations. Okay, so this basically, we pose this problem in the end becomes a distributional robust optimization problem. We solve an optimal minimax detector. So you try to find a detector that have the smallest loss. So what is going to be the loss function here? We consider the traditional type 1 plus type 2 error, taking expectation with respect to the true distribution. The true distributions are within these uncertainty sets we constructed. This original formulation is a non-convex formulation, non-smooth because of 0-1 loss. So what we have achieved is mainly two results. The first is we can show, using some tight convex realization, we achieve nearly optimal detectors. And The other main approach, main results is we have a computationally efficient reformulation. So the most important idea behind this is this is a mini-max problem. So for the max part, for the minimum part, we can find a closed form expression for the optimal detector. So given any true distribution pair, P1 and P2, we can find a corresponding optimal detector. And then this problem becomes just solving the worst case the distribution, and this worst case distribution can be given as a convex optimization problem. So as you can see in the right-hand side of the slides, in the end, what goes into this optimization problem is going to be you take pairs of samples from each of your training classes, looking at the pairwise distance between them. It's sort of like forming some kind of gram matrix using kernels. So we're imagining this can be generalized to other type of kernelized versions. And the nice thing about the structurable formulation is it's pretty much independent of the dimension of the data points. So we can handle high-dimensional data. And on the other hand, the convex formulation results in a very good computational complexity. It's on the order of log of n1, which is number of samples for the first class, and the log of number of n2, which is sample for the second class. And we also have a pretty nice statistical interpretation for this approach. So in the end, what basically becomes is you look at these two uncertainty sets. You look for the two distributions that are close to each other in certain statistical metrics. So what this metric is, it really depends on what your canonical relaxation is. For example, if you relax the 0-1 loss using exponential loss, this is going to lead into K-out divergence type of closeness vicinity. Okay, so this actually generalizes the earlier work by Juditsky and Nemirovsky in 2015. And this is a general framework. So as a first step, we demonstrate this for real-time detection of human activities. So if you're interested, please stop by our poster, which is poster number 2 downstairs. Thank you very much.
Hi, I'm Yi Zhou from Duke University. I'm going to talk about convergence of cubic regularization under Euler-Civic property. This is joint work with Zhe Wang and Professor Yingbin Liang from the Ohio State University. So cubic regularization is an optimization procedure where at each iteration, we build an approximation model of the function based on the Taylor expansion. And the next iterator is said to be the minimizer of this approximation model. This algorithm has been shown to converge to second-order stationary points in non-convex optimization and can escape strict saddle points. Existing works focus on convergence of cubic regularization in non-convex optimization, and a global sublinear convergence has been established. Other works studied the convergence under certain types of local geometries. However, these geometries correspond to a limited function class. In our work, we explore the convergence rate of cubic regularization under the more general Euler-Civic property of the objective function. The Euler-Civic property basically says that within a neighborhood, the function value gap is bounded by the gradient norm to the power of theta. Here, theta is called the Euler-Civic exponent. Many functions have been shown to satisfy this property with different choices of theta. And our result shows that the convergence of cubic regularization to a second-order stationary point ranges from sublinearly to superlinearly depending on the parameterization of the Euler-Civic exponent theta. Essentially, a larger value of theta implies a faster convergence rate. So this theta kind of captures the sharpness of the local geometry of the objective function. We also show that the convergence of function value also ranges from sublinearly to superlinearly depending on the parameterization of the theta. And we also study the optimization path of cubic regularization, and we show that the entire optimization path has finite length. And it is also absolutely summable. This result strengthens the existing result where only cubic summable is established. We also show that the convergence of the variable sequence, the convergence rate, also depending on the parameterization of the Euler-Civic exponent theta. And we can further compare the convergence rate between gradient descent and cubic regularization method. We can show that a cubic regularization method in general has a faster convergence rate. And moreover, in a wide range of parameterization of theta, cubic regularization converges superlinearly, whereas gradient descent converges only up to linearly. So if you are interested in our results, please come to our poster number 4. Thank you very much.
This concludes the session. Thanks for everybody for attending and your attention.